Hello everybody, Adam Lusek here, and today we're going to be talking about fine-tuning embedding models for retrieval on domain-specific data. As we've come to know, embedding models are really the backbone of retrieval augmented generation pipelines, where we rely on embedding models to take our unstructured data, convert it into dense vector representations, which allow us to run semantic similarity retrieval across all of our unstructured data. Generally, the retrieved documents are then passed to a language model, where the language model augments its generation via the context that's retrieved from our knowledge base. And while you might believe that it's the language model that determines the fidelity of a RAG pipeline like this, I personally believe that it's more reliant on the actual accuracy of our retrieval step. This is mainly because the language model only understands contextually how to answer based on our knowledge given the retrieved documents from the search step. Thus, the better that we can tailor our retrieval step to more accurately and consistently return back the right documents at the right time, given what queries our users are putting into, the better our answers from our language model will be, since it's relying on only the most accurate of retrieved data. Despite this understanding, most RAG pipelines actually rely on standard and generalized embedding models, things like OpenAI's or other open source models that handle just a wide variety of data. And while these models are very good at what they do, I found that they suffer in performance when applied to domain-specific or niche content, often failing to really retrieve the most relevant or useful documents from some end user perspective. In the past, I've covered creating linear adapters for existing embedding models to better represent at runtime your query's embedding within your vector database for semantic search. However, since then, I've gotten a few requests and some specific notes of folks interested in learning about full fine-tuning of embedding models. So that's exactly what we'll be going over today. I'm going to show you the process I took to take my synthetic dataset of labeled questions and corresponding text chunks to fine-tune an embedding model to perform up to 60% better in some metrics on document retrieval, hopefully providing you the tools and understanding needed to apply these techniques to your own specific knowledge bases and domain-specific applications. As a quick note before we start, I want to give a lot of credit to Philip Schmid and his fine-tuning embedding models for retrieval augmented generation blog post here. I've taken the methodology and approach that he uses here, as well as a decent amount of the code, and adapted it for my own specific use case here, but a lot of it comes directly from this blog post. I'll have this linked in the description below. Definitely give it a read, some really great stuff. So with a lot of the initial context out of the way, the first thing that we have to do is talk about our dataset preparation. In this case, our main goal is to improve the performance of an embedding model on unseen queries across an existing knowledge base. What this means is that we're assuming that we already have an existing set of documents that have been chunked in some way. So that is usually going to be your knowledge base for your RAG pipeline, and what we're aiming to do is improve the embedding model's performance on questions that come in to more accurately retrieve from the existing knowledge base. I'm making this distinction because, importantly, this method is not quite primed for actually generalizing towards different knowledge bases, or if you're going to add in additional documents into an existing knowledge base. This is more so meant to push the performance of some existing one, and of course, further training can be done as that knowledge base is expanded or contracted. So in our specific scenario, I chose the industry of law, and what I'll be simulating is a knowledge base that consists of these 10 court case opinions. These cases come in the form of opinion documents, essentially nice long write-ups of exactly the proceedings and kind of final determination of the court case. So in our current hypothetical, what we're simulating is having 10 of these documents and then running retrieval augmented generation over all of these. So as a query comes in, this might be something like a question and answering system. It will try and retrieve the most relevant piece of one of these 10 court cases and use that as provided context for answering whatever question you have. While this situation is specific to law, you might think of this yourself with kind of just your own documents. Whatever documents you have chunked and stored in some sort of vector database would be considered your knowledge base. But more importantly, from this, what I've done is I've gone ahead and created question and chunk pairs. What this means is that for a given question or a query that might come in, what is the corresponding chunk of your chunked knowledge base that would be used to answer that question? Across our knowledge base of 10 court cases, what's gone on to create these pairs is we've turned these all into text and then chunk them with a recursive character text splitter at a chunk size of 400 characters. And then for each corresponding chunk, what I've done is ran this through a batch job of GPT-4o to create a corresponding question that can be answered using just the information provided in this text chunk. After some deduplication and some filtering based on semantic similarity, what I ended up with was about 6,500 rows of these corresponding chunk and question pairs. And this simulates essentially the perfect response from a retrieval system. So given a question that's asked like this, we would expect to see this chunk as the specific return chunk that's the most relevant. Now, while I've gone ahead and actually generated these synthetically, the hope would be that you would actively be collecting the user queries as well as the return chunks and some sort of logs from your given retrieval augmented generation application. Then, given some sort of labeling of how accurate the retrieved chunks are or which specific chunk is the most relevant, that data can then be used for this kind of fine-tuning. To touch briefly on some of the other dataset structures that are commonly seen for fine-tuning embedding models, we just touched on the positive pair dataset that has a pair of related sentences. What you might also see are things like triplets that include an anchor, a positive, and a negative. In this case, our anchor would be the question or query that we're asking. The positive would be the corresponding positive document that would be used exactly and most relevantly to answer that question, and then the negative would be some sort of unrelated document. It's common practice to use this triplet approach because what you can do is use something called a hard negative, which is a very similar document, yet critically different or unhelpful to actually answering your anchor or your expected query. And during training, what we'll see is the embedding model is going to try to learn to represent the anchor more specifically with the positive and further away from the negative. So if you have really good examples of close together sentences, as well as one that might be similar yet not close, this can really aid in the fine-tuning process. What we'll see, however, is that the actual loss function that we're using in our training approach will take our positive pairs, treat them as the anchor and the positive, and then sample randomly all of the other documents, since right now our dataset only has one specific question and a corresponding document, so it'll sample all of the other documents as negatives. So this approach is relatively the most straightforward way to get started with some of these things, as it tends to be a little bit easier to actually gather the question and corresponding text chunk being retrieved, rather than putting together more of the embedding model specific data structures. So essentially what we have now is our positive pairs that we've kind of simulated collecting from user questions across our RAG app, which might be some sort of retrieval based on these 10 legal documents. The few steps that I go through to actually prepare this is using the datasets package from Hugging Face to load it directly from Hugging Face, where it is currently being hosted. And then what we're going to do is clean it up a bit. So I rename the question column to the anchor, I rename the text column to the positive, the text being the chunk, and then I remove all of the other random metadata that I have. However, one specific note, I do keep the global chunk ID. On top of all of this, I add in a quick ID column that is agnostic of all of the other IDs and will just range from the entire length of the dataset down. Giving that a quick shuffle and splitting it 90% to 10% train test split, we then save those to quick JSON files just for easier downstream processing. So with most of our dataset prepped and ready, what we need now to do is choose a base model and also evaluate its current performance. For this specific demonstration, what we're going to be using is the ModernBERT Embed base from Nomic AI. Nomic took this ModernBERT base model, which by the time this video comes out, I should have a video which will pop up on the screen right now, explaining a lot about bidirectional encoder representations from transformers or BERT models here. But what they've done is they've taken that base model and trained it on the Nomic Embed dataset. This means that it is prepped and ready to be used as a sentence embedding model, so able to take some sort of source sentence and compare the similarity of it to other sentences, which, as we know, is how semantic similarity-based search and vector retrieval works. More specifically, what this model is going to do is take in an input sentence or document and return back a 768 dimension dense representation vector. Essentially, a list of 768 numbers that capture the semantic meaning of whatever document or sentence is input. Our hope then is, of course, to take the process of semantically representing ideas, concepts, and documents as numbers and tune it more towards understanding our current knowledge base. But to be able to see if we are successful at that, what we need to do is understand the current model's performance. So what we need to do is do a little bit more data preparation to create an information retrieval evaluator. The IR evaluator is a built-in evaluator into the sentence transformers package, and what you're able to do is provide in some data to get the most relevant and necessary information retrieval metrics back out. We'll dig into exactly what those metrics are in a second here, but more pressingly, what we need is 3 key data structures for the IR evaluator to actually work. We need to create a corpus dictionary that maps IDs to documents, a queries dictionary that maps IDs to questions, and then a relevant docs dictionary, which specifies which corpus documents are relevant for each query. Essentially, we're creating a bunch of dictionaries that map a bunch of IDs together so that we can run a lot of these metrics a lot more efficiently. So to do this, what we do is we load our testing and our training data set, and then we combine them together to start. This is a very important point. What we're going to be doing is creating this corpus of all of our possible chunks. The reason this is specific to call out is because what we're doing is we're training using the existing text chunks. So we're not training a model to generalize towards unseen text chunks. We're training to optimize on existing knowledge bases. This optimization objective that we're aiming for here is very different from some of the other machine learning training concepts where you might be thinking to train a model that can generalize towards those unseen documents or additional documents that you might be adding to your knowledge base. This is different because what we're doing is more optimizing towards unseen questions on an existing knowledge base. Which to test that, what we do is format our queries purely from the test dataset. So while our corpus includes all of the text chunks, our testing dataset will only include the questions from the test split. We then create the aforementioned mappings here with respect to global chunks. The reason I'm paying attention to this is because in my data structure, I actually have multiple questions that were generated for individual chunks. So a chunk can have between 1 to 4 relevant questions attached to it. So taking into consideration our global chunk ID, we can handle cases where multiple questions can refer to the same text chunk. So with the respective dictionaries that we have here, what we need to do is also talk a little bit about a second technique that we'll be applying within our evaluator and training, and that is Matryoshka representation learning. Taking inspiration from the Matryoshka dolls or Russian nesting dolls, Matryoshka representation learning is a technique for training models to encode information at different granularities within the same embedding vector. This approach teaches the embedding model to create representations with higher level information and coarser information packed into the earlier dimensions. So literally in the array that is our vector, the first, say, 8 to 64 dimensions, and then finer details in the later dimensions. The goal of this is to be able to actually take our vector, which in our case is going to be 768 dimensions, or 768 numbers long in a list or array or a tensor per se, and be able to actually perform some sort of truncation on that. So reducing the dimensions from something like 768 to maybe 256, and being able to actually maintain comparable accuracy. Well, this technique isn't crucial to actually the general fine-tuning of our model. It's something useful to actually include because you can use these truncated vector representations for increased efficiencies in deployed situations. What's going to happen then is our embedding model is still going to output the same size vector representation of our text, but what we can do is chop off some number of dimensions off of the end of that vector and still be able to use those truncated vectors. The use of these different truncated vectors comes into play across a few different scenarios. Obviously, there are efficiency gains of being able to store shorter yet still comparable in accuracy vectors in something like a vector database. Shorter dimension vectors, like those that are 64 dimensions, are much, much easier and more efficient to store, as well as it's quicker to run semantic search over. But then you can still use the larger dimension vectors for your more granular analysis. So from the Matryoshka representation learning paper here, they propose a scenario where you might store a bunch of documents in lower truncated dimensions and then create a short list at runtime of potential documents given your search, and then you can re-rank those based on the larger or higher dimension representations. On top of individual use cases like that, another benefit is that we can tend to get the same, if not very, very slightly diminished performance from lower dimension representations using this training method. So while not necessarily needed for the fine-tuning of these embedding models, adding in MRL is very lightweight and easy to do and can help with all sorts of these downstream things if you're looking for further efficiencies, which in this case, we might be. So we'll go ahead and implement this into our training as well as our evaluation, which we'll finally get to defining here. Essentially, what we're going to be doing is creating 5 different evaluators for each truncated dimension. So we're going to be using 768, which is the base model's largest output dimension, and 512, 256, 128, and 64. It is important to note that we are listing these larger to smaller because during training, what we'll be hoping for is to create first that dense, rich representation across all of the dimensions, and then forcing the language model down to learn and include only what's most important as it gets compressed into lower and lower truncations. But with our candidate dimensions here, we're going to be creating for each dimension an information retrieval evaluator, passing in our queries, passing in our corpus, passing in our relevant docs, and passing in each one of our dimensions. All of these evaluators are going to be appended to this list here, which is turned into a sequential evaluator, which will essentially just go through all 5 of these evaluations in sequence at each one of these truncated dimensions. What exactly are we going to be evaluating then? Well, a whole suite of information retrieval metrics. So let's go through each of these real quick and explain how to interpret them. Starting with our most fundamental metric, that would be accuracy, we're going to see first off that these are all going to be metrics at k. The at k represents how many retrieved examples are actually popping up in our retrieval system. So we can see accuracy if only 1 is returned, or accuracy if 5 documents are returned. That's what that at k represents. But accuracy is going to measure the presence of at least 1 relevant document in our top k results for each query. For example, an accuracy of 0.9 would indicate that 90% of our queries successfully retrieved at least 1 relevant document within our top k results. Our most important metric that we're going to be looking at is going to be the NDCG, or Normalized Discounted Cumulative Gain. NDCG essentially captures both the presence and positioning of relevant documents in these ranked results at k that we are retrieving. The key here is that the relevant documents appear lower and the ranks contribute diminishing value to our overall score. We're especially going to be paying attention to this one because it'll show us kind of the combination of when relevant documents are appearing in our searches as well as those rankings. So we obviously want to increase the amount of times that documents appear that we want to appear, as well as increase the rankings of those documents. So this is going to be our true North Star that we want to optimize towards. But along with this, we're going to have a few additional metrics to look at. Precision and recall at k are complementary to each other and are going to kind of show our retrieval effectiveness from 2 different perspectives. Precision at k is going to measure the result accuracy by calculating the fraction of relevant documents among our retrieved top k results. For an example, if our precision at 5 is 0.8, that indicates that 4 of the top 5 results were relevant. Our recall at k is going to quantify the retrieval completeness by measuring the fraction of all relevant documents found within the top k results. So for example here, if we have a recall at 10 of 0.7, that indicates that 70% of all relevant documents appear in the top 10 results. In a way, these are going to be measuring similar things, but precision is more of that local view, just looking at the current retrieved set, whereas recall is considering how many of the total global set is retrieved within that top k. Our last couple metrics that we can capture, first starting with the mean reciprocal rank, the MRR is going to be more focused on the first relevant document in the ranking and its specific position. So the reciprocal rank for a query is going to be 1 over the position of the first relevant result. In this case, we want to make sure that our first relevant document is ranking highly, so we want a higher MRR, which in the case of this, if our relevant document is in the first position, would give us an MRR of 1. Mean average precision then, our final metric, provides a comprehensive single score assessment of ranking quality, essentially starting by looking at where each one of the relevant documents in a given set ranks, and then calculating its precision at that point. These precisions for the given query are then averaged to create the average precision, and then the average precisions across all of the queries are averaged once more to create our mean average precision. So this will give us a comprehensive overview of how well our system is ranking the relevant documents. To quickly summarize, all of these together provide a comprehensive framework across multiple dimensions. We have basic retrieval capability with accuracy, ranking quality with the NDCG, result set precision and completeness with precision and recall, first relevant result positioning with MRR, and overall ranking effectiveness with mean average precision. So after running our model through the evaluator and then printing it out a little bit nicely, we get our base results. These are of course going to be at each truncated dimension here. So we see that each one of these results at each of their Ks is under their respective dimension truncation. Our main metric of interest is going to be our normalized discounted cumulative gain at a K of 10, which is going to be shown across all of these different dimensions. And we can see that it starts to drop off at these lower dimensions here, and we're getting about a 0.44 from our highest dimension as our base result. Just to mention real quick, this sequence score down here is going to correspond to the NDCG at 10 of 64 dimensions. But with our base results figured out here, now we can move on to actually fine-tuning our model so that we can run some more evaluations and compare. With all of the hard prep work out of the way, training the model is actually not going to be so bad. We already have the dataset and the evaluator determined. Now all we need to do is figure out the training argument and the loss functions. We already have our model picked out, but we're just going to load it once more here in this code block with a few additional arguments. We're first going to be implementing a scaled dot product attention, which is going to give us some GPU-based efficiencies since I ran this in a collab notebook. We're also going to attach a quick sentence transformers model card along with all of this stuff so that when we upload this to the Hugging Face hub, it can have a nice base template that we can fill out for all of the information and all of the training information that's automatically collected. With our model loaded and ready, we need to do that loss function selection. So loss functions really are what's used to guide neural networks and the training that goes into them towards the different improvements that they're hoping for. Generally, what happens is a loss function will compare the current performance with the expected performance, calculate the difference or loss, and then the value of that and how big that value is determines the direction that we are actually optimizing towards. This is a drastic simplification of how training and losses kind of work, but it should give you a bit more of an intuitive detail if you're new to the system. Sentence Transformers has a whole lot of different loss functions built into the package that we can take advantage of based on how our dataset is structured. Given that we have anchor and positive pairs, and that's about it, the documentation recommends the multiple negatives ranking loss. This is going to take in a batch of pairs. And what this is going to do is then for each anchor positive pair, that is going to be our given anchor and our positive, and then all other pairs are going to become negatives. This is a very efficient way of actually taking advantage of scenarios where we only have anchor positive pairs, reusing all of the others for those negatives. This will then aim to tune our model closer towards representing the anchor and the positive pair more closely together with regards to making sure that they're not related to any of the batched negative pairs. But not to be outdone with a single loss, we're also going to implement the Matryoshka loss, which is going to wrap around our multiple negatives ranking loss as a wrapper. This will allow us to use our original loss function at various different embedding dimensions. So this is going to help us because we want to train a model where users have the option to lower the embedding dimensions. Essentially just applying the multiple negatives ranking loss across all of our dimensions and then weighting them so that each one is considered across our training process. So this joint loss function will optimize our model towards improving our performance across all of our metrics, across all of the different dimensions using our base loss function. So now with our model and our loss functions defined, what we need to do is pass in all of the other good hyperparameters that the trainer is going to expect. These are relatively standard hyperparameters, as the sentence transformer trainer is going to be also a wrapper around the transformers trainer. So I'm not going to go into too much detail of what each one of these are, but let's hit on the highlights. First up, most of these were grabbed directly over from Philip's blog, so once again a reminder, definitely check out his great work over here. But what we can see here is we're going to be running 4 epochs of training, meaning that we're going to run through all of our training data 4 times. We're also going to have a per device training batch size of 32 with a gradient accumulation steps of 16. We're going to make sure that our batch sampler does not have any duplicates, once again for our loss function here. And finally, we are going to be scoring and saving the best model that performs at the 128 dimension for the NDCG at 10 metric. So with our arguments defined, what we can do is combine it all into a trainer. So within our sentence transformer trainer, we pass in our model, our arguments, our training data set, specifying the positive and the anchor, our loss function, as well as our evaluator, and then we start the trainer with trainer.train. Within this same cell, I also have trainer.saveModel, which at the end of the training will save the model based on our best criteria metric. Looking at the logs, this took only about 6 minutes to fully train, and once that was all done, what I did is I used the model.pushToHub method and uploaded it to Hugging Face. So you can see the exact model that I trained here uploaded on my Hugging Face profile here, which I'll also have linked in the description below. But with our trained model saved and uploaded, what we can now do is run the model through our same evaluator and get the updated metrics from the fine-tuned model. Zooming in a little into this quick comparison table that I have here, looking at our main metric of interest, the normalized discounted cumulative gain at 10, we can see across our dimensions, we had massive improvements on our testing set. This is great to see because we can say now with confidence that our training generalized towards unseen queries on our existing knowledge base, which means that we should see an improvement in performance across the board of our retrieval system on subsequent questions that are asked given our current information and unstructured data that we have here. It's also impressive to see that with just a little bit of training, we can get as much as almost 50 to 60% increases across some of these metrics here. With a specific note that our truncated 64 dimension representation is almost as good as our base model's 768 dimension representation. So not only do we have a much improved across the board system for our current setup, we also have a way of gaining those additional optimizations through truncation methods from the Matryoshka representation learning. As I continue to mention, however incredible these improvements that we've gotten, further testing would have to be ran to understand how well this model may generalize towards any unseen documents outside of our existing knowledge base. Using this model then is relatively straightforward. All you got to do is install the right packages, and then you can import from sentence transformers directly your model ID. Truncating the actual dimensions out is also super easy. Now that we have the ability to do this and we've trained our model specifically for this, all we have to do is pass in the truncate dim argument here. So I put in 256. So after encoding a few of these sentences here, I have an example query from the dataset, as well as the corresponding positive and a random excerpt here. And we can see that our output here is 3 by 256. So one vector for every single sentence here, that is 256 dimensions. Calculating the similarity then across the first sentence with the first 3, we see that the first sentence is of course going to be perfectly comparable to itself. And then we see a score of 0.58 and 0.004 with respect to the positive and random excerpt. Comparing this to the base model's output of 1.6 and 0.47, we can certainly see that there have been some changes. But with that being said, I hope you learned a little bit about how to fine-tune embedding models yourself and how easy it can actually be to set these up for your own domain-specific data. I'll of course have all of the resources linked down in the description below, as well as the original blog post that inspired this all from Philip Schmid. With that being said, hope you learned something interesting today. If you like the video, like the video. If you have any questions or comments, leave them in the comments below. And if you want to support the channel and see more like this, consider subscribing. Thank you and have a great day.